So thank you so much for the opportunity to talk. My name is Eric Rosenthal. At Mass General Brigham, I am the medical director of our neuro ICU, and I also direct a center called the MGB Neuro AI Center. These are my disclosures, in bold are the ones relating to this talk. This is what I'm going to largely talk about today are data silos. This is sort of the situation that I think in the room we fear. The problem is it's even worse than that. It looks a little more like this. And I think the goal is to get to a place like this. So, it has taken us 2 years as part of a project I'm part of to develop not just the data and the standards, but also the tools to meet the needs of an AI lifecycle. We've done this through a fairly large consortium of 20 hospitals, 14 of which are collecting data, through a program funded by the NIH's Bridge to Artificial Intelligence program. And within that program, we oversee, with a set of investigators, the CHORUS program, which has its goal to develop a national infrastructure for clinical care AI. What we secretly didn't tell the NIH is that we are all intensivists. So sometimes the clinical care AI slips to critical care AI, but if we're in the room, we want to set this as a model for clinical care in general. And one of the reasons that I think critical care is really ideal for this is that we deal with the most high-dimensional types of data. So our goals in this program, now that we're about halfway through our cycle, is to develop software tools and standards for data, and then harmonize a high-resolution data set, which is multi-center, and that inures us against problems with robustness with models that are developed at a single center. Not just that, but the critical ethical, legal, and regulatory guidance, and then the educational tools so that we can build our own community. To standardize data, you need a Rosetta Stone of sorts, and there are different standards in the field. These are the three that we are using. For electronic health record data, the Observational Health Data Science and Informatics standard, Odyssey, has an OMA common data model. For imaging, I think many of us are familiar with the DICOM standard. And for waveform data, the WFDB standard has been articulated through the MIMIC project that many of you may also be aware of. These standards don't always talk to one another, and one of the goals of our project has been within the Odyssey community to create links for imaging and waveforms to be embedded in the sort of tabular representation of data. There's a QR code I'll show at the end, but our colleagues and we have developed a sort of plan for sites on the left to generate data, get it, standardize it, link it, DID it, and then submit it to a central cloud where it can not only be ingested but assessed for its quality, and eventually approved. And at each step of those, we have different types of tools that facilitate, and we post those tools as open source. So this is an example of, you wait so long for data to accrue, and then when it's ready, it begins to accrue. In the audience is Gilles Claremont, who oversees, with Andrew Barros, our data acquisition module. And you can see it took almost a year or two for data to start to accrue. But when we think about measurements, a measurement might be an example of a RAS score, pupil function. We have now, from about 30,000 patients, about 250 million rows of measurements. So it gives you the sense of the power of moving beyond a case report form, beyond a CRF. This has taken a lot of work to develop an enclave-based collaborative cloud to be a sort of data hub. And I won't go through here, but you can see sort of the areas in the data hub that are required on the bottom right. For each site, secure ingestion to firewall exceptions and so forth. And on the top left, an external place that we can do ML work and quality and checking in the middle. This is an example of some of the rich tools that the Odyssey program really has pre-developed and can be modularly utilized. The ARIES data quality dashboard. This shows our population. So we just got above about 30K patients. We have another 2 years to get to our goal of 112, and I think we'll hopefully see that curve inflect more vertically. And then on the top middle, you can see the data quality issues, where you don't want garbage in, garbage out. You really need the data to be of high quality. And then on the right, you can see sort of the need to look at different types of demographics and so forth. In our data set, we have a nice cadre of patients from neonatal ICU. So you can see in the right, in the middle there, that blue plot shows a histogram, including a lot of patients who were born more recently. Data quality issues include completeness. Did a site attempt to upload a certain type of data that it conforms to a standard? So for example, in our ethnicity table, we have a few data elements that, where the ethnicity is not a normal ethnicity, it's a measurement from a flow sheet. So that's conformance. And then plausibility, which means, your blood pressure, we hope, should not be, 1,000, right? On the right, this data from my center, you can see most patients, for example, should have a blood pressure, we hope. I don't know who the 0.06% are that don't have a pressure. But what also comes with this is a great deal of number of measurements. So a patient in ICU may have 1,000 blood pressures in the electronic health record. And that's not waveforms. That's just what a nurse records, which just gives you an incredible appreciation for that level of work. Imaging is a particular, sorry about the cursor here. Imaging is a particular challenge of ours. So there are tools to redact not just the overlays that are present in image headers, but the pixel level data that may be burned into an image. Something called secondary capture, which is when a patient is at another hospital and referred. Those are high-risk scans that are often needed to be removed to lower the overall risk. And then there are other types of studies like dosing reports or fancy 3D reconstructions, which are also high risk. But beyond that, you need to have an optical character recognition tool to redact, and typically a workflow for human verification. We're very interested also in geocoding, not to share a person's address, but to understand the features in the location in which they live. So in a pilot study, we developed a pipeline to extract location. This is my home state of Massachusetts. On the bottom left is the social vulnerability index, the summary score. It has several components. And you can see that according to sort of geographic regions that are more urban. And on the right, you can see rates of geographic rates of something like withdrawal of life-sustaining therapy. So, data like this can tell you about pollution. It can tell you about, the economy of where a patient is coming from. You don't need to share someone's address to know sort of the local vulnerability in the environment in which they live. And then in terms of tools for visualizing data, this is an example, a set of tools. One is an integrated viewer we call IVE, where modularly we can sort of drag and drop certain tiles for looking at either sort of annotations or imaging. The idea would be we'd look at a chest X-ray and try to understand, our CT. Does this patient have a PE? You'd want to look at an EKG. You might want to look at a CT image and so forth. Another tool would be a cohort adjudicator, where you might want to click in the top right those colorful buttons, AFib, not AFib. And there might be another type of tool where you might want to read types of notes and then tag these as whether it meant the patient was symptomatic or something like that. And in a third tool, when submitting text, which is something that is not a main part of our project, but we're experimenting with. This is a tool for actually de-identifying data where you can label data. John Doe is a person, a date and time, you can label it as such. And you can actually look using different models like the I2B2 Roberta model to slide the sensitivity and specificity to say, we really want to catch every piece of PHI, so we're willing to lose some data or not. And then lastly, we want tools where we can bring models in to evaluate their validity. We know, for example, from the epic sexist model that some models don't validate, so we want to be able to upload the data and get the ground truth and say, these 4 cases did in green and others did not. I'm going to go more quickly through tools to promote trust. It's not just bringing data together, it's obviously how we look at data. And so measuring and managing confounder space is critically important. And having that data, for example, social vulnerability, location, marital status, are key confounders that we might want to use to sort of break out how we train and test models so we can train them in the old and make sure that they work in the young. There are other tools, to promote trust, like ensemble learning or stacking, in which you build models and then you use those models themselves to sort of retrain again iteratively. And then interpretability tools. I showed the data about withdrawal of life-sustaining therapy. It should be meaningful to everyone in the audience. I don't know all your personal values, but that in our data, the third most likely factor relating to withdrawal licensing therapy is whether you're married. And so that's a conversation for, personal conversation. But next to that are also things like race and education and income and so forth. And you can look at that on the right for a population in purple. These are Shapley values. And you can look at them on the left for a single individual, top right. Or this individual was highly likely to have withdrawal of licensing therapy because of advanced age, which is on the top in red, pointing to the right. On the bottom model, the patient was younger and had a lower initial severity score, was less likely to have withdrawal licensing therapy. And then we can also look at subgroups to understand if models that are trained in, my population of neurocritical care, trained in TBI, do they work in hemorrhage? Trained in the young, do they work in the old? Okay. And then lastly, this is something we're starting to experiment, which is bringing AI tools to the bedside. So will clinicians and patients trust a model, even if we think it works really well? So what we started to do is develop tools that we can select a patient in history, almost do a simulation with a patient, and show, or with a clinician, and show them tools, sorry for the speed here, show them these types of Shapley values, what the prediction is based on, interpretability, and then sort of a gauge. And we're going to start this process of working iteratively with clinicians and patient surrogates to understand, even if we do this, will they really trust us? Will they want to rely on this level of data? So just a few people to call out in the audience. Robert Stevens, Jill Claremont, Rishi Kamaleswaran, who you'll hear from, Ian Wong, and many others. Just want to thank everyone for their incredible dedication to this project. Thank you.
Thank you so much, Dr. Rosenthal. I'm Smitty Hevner. I have the privilege of co-moderating this session with Ashish. I want to welcome next Dr. John Sevransky from Emory University.
Well, thank you very much for the opportunity to speak to this group. And I am a clinical trialist. I am by no means an expert in AI, and I want to tell you a little bit about why I'm happy to hang out with people who are expert in AI, and maybe talk a little bit about how those two regions might intersect. So these are my financial disclosures, but I've already told you my biggest disclosure, which is that, again, I'm a clinical trialist, and I can say AI, but I'm fortunate to have some smart colleagues, and I'm going to show you the work of some of those smart colleagues moving forward. So every day when I'm on clinical service, there are families that entrust the care of their loved ones to me and my colleagues, which includes nurses, pharmacists, respiratory therapists, advanced practice providers. And one of the things that's clear when we care for those patients is that a fair amount of what we do is driven by experience and by training. And some of what we do is driven by data. Some of what we do, and in the past 15 or 20 years, there's been large numbers of clinical trials groups that have started to look at the types of things that we do on a daily basis, and maybe 40 to 50% of what we do on a daily basis is driven by evidence, with the rest driven by experience. And that's an awful number. It's better than it was when I started training, but it's probably not anywhere near where we'd like it to be. And one of the reasons why I think we've had so much trouble generating evidence to care for patients is that it takes lots of time, lots of money, clear funding, and a vision to get from having a good idea with biologic plausibility to having a drug or a therapy that you can work with patients. And this can take 20 to 25 years, even in good circumstances. COVID may have pushed that up a little bit, but it still takes an awful long time to get from an idea to something that's going to help the patients that we all see. And to further complicate that, starting with things like cancer, we now have evidence that perhaps not everybody has the same response to every therapy. And there are some people that perhaps we ought to be treating different from others. So it's really complicated to improve the care of patients. And I've given way too many talks where I go over things that people have spent a lot of time and effort doing, and it hasn't really helped the patient in the end. It's told us what not to do, which is helpful, but it's really, again, it doesn't help me do things better, and oftentimes people will refer to sepsis trials, and I've been to places trying to get funding for sepsis trials, and oftentimes people will say, we're not gonna fund that trial because you can't find something that works. And so there's a lot of time, a lot of money, and we've done recently, a few years ago, we spent a lot of time, a lot of money through the Discovery Research Network to show that vitamin C, thiamine, and steroids didn't work in patients with sepsis and cardiovascular or respiratory failure. I don't think it will come to a shock to anybody that doing a trial in this century is extraordinarily expensive. Ann Drury at Wash University had some wonderful preliminary data on warming patients in sepsis. And we got a group of people together who were really, really good at trial design, really good at enrolling patients into trials, and came up with a budget that we thought was reasonable, which was about $26 million to test it in a phase 3 trial. And we spoke to every single program officer at every single NIH institute and the DOD, and got 28 or 29 resounding no's. We're not going to spend money on this. And it's a wonderful idea that unfortunately was not able to be funded. So it'd be awful nice if we had a better way to do this. And so why would you use AI for clinical decision support? And to do clinical trials with this? Well, potentially, it could identify patients with you. It could potentially phenotype or subphenotype patients. And potentially, if the phenotyping were simple enough and didn't require really expensive labs, then maybe you might be able to do it outside of traditional academic institutions where the overwhelming majority of clinical care is delivered in the US and elsewhere. So I mentioned I had some smart friends. He actually looks a little different from this. He shaved his beard between the time I put this up. But one of the things I do sometimes is evaluate manuscripts for critical care medicine. Pat Lyons, who came up with some criteria along with some other people on our journal to come up with when we should think about prediction models and when they might be useful. And I hesitate to say this to a room of people who are really smart about prediction models and about AI, but for a clinician who knows nothing about it, what they're mostly interested in is whether or not, if you have the model, the prediction model, whether it will change what a clinician does or what happens to the patient. And I don't mean to demean it's extraordinarily difficult what people do to put things together, but for somebody who knows nothing about it, they care about the output on their day-to-day work. So again, to change behavior, to change what you do, you want to have evidence that using a model or using something will change either the outcome for the patient or the outcome for change what the clinician might do. So there are lots of ways that you could integrate AI into an electronic medical record for a clinical trial. And one of my smart colleagues, who I believe is sitting in the audience, did a nice job and has published in 4 or 5 different journals his validation of looking at vital signs, which even in non-high-tech places will have vital signs, that patients with sepsis have different trajectories that you can elucidate by just seeing what their vital signs might be. And additionally, he's shown that these patients, depending on which subphenotype you have, might have a differential response to fluids in retrospective data. Again, you don't want to change what you do in your hospital unless there's clear evidence that either for patients similar to yours or for patients in your hospital that things work. So Siva and his team did a wonderful job of creating the PRECISE trial, in which they very quickly they built their prediction model and they integrated it into the EMR. I cannot tell you how they did that, but Siva's in the audience, and if you have questions, please ask him, so that it will pop up on the screen that if somebody does have a particular subphenotype, that data at our institution and a different institution, if you had that subphenotype, you did worse if you got normal saline compared with a balanced crystalloid. And how this trial works, and it's wonderfully smart, is that he did not switch the patients. He just has a pop-up on the screen that says, if you turn out to have a patient in that subphenotype and the clinician orders normal saline, you'll get a message that will say, that we've got some data suggesting that your patient might do better with a balanced crystalloid. The clinician can ignore it if they have brain injury or something else where you might not want to give them a balanced salt solution. They can completely ignore it. And this answers, I think, both parts of the Lyons criteria. It both checks to see whether the clinician will follow this, and it will check whether or not the patient will do better. So I am hopeful that your talents will help people like me who try to design better clinical trials to design better and cheaper clinical trials that will help those patients that up till now we probably aren't doing as good job as we might because we don't have enough data to support that. So I hope again that we can leverage the EMR to provide clinical decision support if and only if it works to either change our behavior or help patients, and that we shouldn't routinely use these until both of those things have been shown. And I really appreciate the opportunity to talk to people about something that likely most of you know much more about than I do. So thank you.
Thank you very much, Dr. Sevransky. It's great to have that perspective. Continuing with different perspectives that are important to consider, we're going to invite our pediatric colleague, Dr. Sanchez-Pinto, to come up from Lurie Children's Hospital in Chicago. Make sure I can get his slides up. Thank you, Nelson.
Thank you. All right. Can I have a show of hands of who practices in a pediatric intensive care unit? Oh, look at you. We're not that, it's almost 50%. Okay, so I have to convince the adult side of the audience that pediatric matters, and for the pediatricians that we need to have a stake in the game, otherwise we're gonna get left behind. This is the first time I have the FCCM in my slide title. I'm getting the convocation today. Very excited about that. So no relevant disclosures. The key points that I wanna make today are simple. One, children are not little adults, even though sometimes we pretend they are. Two, we have an embarrassingly low amount of evidence, and I'll show some figures about that. We often deal with catastrophic needle in the haystack problems in pediatrics, and that's a big issue for us, and I'll show hopefully something to prove that. And honestly, data science and collaborations is the only way that we can move forward. By the way, I forgot to mention, Jen Muszynski from Nationwide was originally scheduled to be giving this talk, and I'm giving in her instead, so if you were expecting Jen, apologies. She sends her regards. Much smarter speaker than I am. So the first point is that children are not little adults, and for many reasons, but even starting from the basic stuff, the physiology is different. So the way you train a model, or the way you may discover some interaction between a treatment and a certain phenotype may not translate to pediatrics when you've discovered that in adults. And an example that I'd like to use to adult emergency medicine residents that come to the ICU and other folks that it's the first time in the ICU is the most basic one, which is breathing. Breathing is one of the most important things that we do in life, and kids have a lot of struggle breathing. And one of the reasons why they have that is because the adult diaphragm is dome-shaped. And the pediatric infant and neonate and toddler diaphragm is flat. And it's very easy to breathe when you have a dome-shaped diaphragm. It is really hard to breathe when you have a flat diaphragm. So even at a respiratory level, that's a big deal. And other things that we always talk about, kids when they're born, they don't have all the alveoli they're going to have as adults. They're still developing throughout their childhood. They have smaller airways, so they get obstructed more frequently. They have a lower FRC because they have cartilage in their rib cage. They have an immature immunity, so their side effects to things like immunomodulation are much different than in adults. So again, kids are not little adults. They're also very susceptible to harm. So if you put we looked at this in this type of figure in different places, but if you put the sort of benefit harm on the y-axis and the therapeutic intensity on the x-axis, most therapies that we use in the intensive care unit, both in adults and in pediatrics, have a U-shaped relationship. And we know this from oxygen, fluids, antibiotics, sedation, PEEP, tidal volume, et cetera. In our task as intensivists, whether adults or pediatric, is to find that Goldilocks, right intensity therapy for each of our patients. And we know that Goldilocks place is going to change, minute to minute, hour to hour, patient to patient. So we have to sort of adapt ourselves. The problem with our patients in the pediatric ICU is that heterogeneity is multiplied, or square sort of cubic from adults because of the age heterogeneity component. And the problem with kids also is that if you lean towards the harm, either you don't do enough of one therapy that the kid needs, or you do excessive intensity of the therapy and you cause harm. That harm is compounded over decades of life expectancy. This is a life expectancy figure there on the right. On blue is the remaining life expectancy based on the age on the x-axis, and as you can see, this is our population. Kids and school-age kids and adolescents and toddlers. Some of these kids will have 6, 7, 8 decades ahead of them of life, and if during their intensive care we're unable to provide them, adequate oxygenation to their brain or adequate perfusion to their brain in say in a TBI situation, or in a kid who has ARDS, we cause ventilator-induced injury. These are lungs that need to work for decades, or these are brains that need to still go through school and have hopefully productive lives. So the stakes for kids are extremely hard. So the room that we have for harm, or the trade-off that sometimes we do between benefit and harm for some of our therapies, has to be extremely tight when you're considering pediatric intensive care. However, even though it's pretty clear that children are not little adults, we often pretend as if they were, and this happens to us. This is a problem for pediatric intensivists, not necessarily adults, but this is a good example. After the OSCAR and the OSCILLATE trials came out, particularly OSCILLATE with the higher mortality associated with using the oscillator in adults with ARDS, there was this sort of slight move towards less use of oscillators in the pediatric intensive care unit, even though we have some evidence that it improves hypoxemia. Maybe not, we haven't done a definitive trial yet, which is currently ongoing. But even before we had a pediatric evidence, we were starting to move away because of the adult evidence. But guess what? Many of the adults that were dying in the OSCILLATE trial were dying from heart failure, myocardial infarction, and kids do not have problems with myocardial infarctions, thankfully. What they have problems with is the lack of alveoli and the lack of room in their sort of respiratory system, where the oscillator may be a potentially good therapy. So again, not a good reason to move away from it until we have definitive pediatric data. Another example is Decadron. Since the DEXA ARDS trial in Spain and the evidence that came out from the COVID-19 pandemic trials, there's been this surge of interest in using dexamethasone in pediatric acute respiratory failure or ARDS, et cetera. But again, as I was saying earlier, we have different profile of immune maturity, different problems with much more significant issues with critical illness myopathy, particularly with the problems that these kids have with their already not great respiratory muscles. So the risk profile is completely different. So until we have pediatric evidence, I don't think we should be adopting data that comes from the adult literature. Unfortunately, we do have embarrassingly low amount of evidence. This is just a pick of the major guidelines that we use in pediatric critical care: sepsis, ARDS, blood products, TBI, et cetera. Almost 400 recommendations, and out of those 400 recommendations, only 14 have moderate quality of evidence, and one has high quality of evidence. And the one that's high quality of evidence is telling us what not to do and not what to do. So we don't have a lot of evidence. That means that maybe we just heard that in the adult ICU, 50% of the decisions are based on good evidence and 50 are not. For us, it's 96% are based on not great evidence, and 6 are based on good evidence that's basically saying don't do that. So it's a problem. But we do perform thousands of natural experiments every day, right? And even though I would like to do an RCT of every single question that I have every day, it's just humanly impossible to do it. It's very expensive. It's very time consuming. So we have to be very selective about the RCTs that we're going to be conducting in pediatric ICU. That means that there's going to be a heck of a lot of questions that we won't have the time, bandwidth, or money to do in a randomized controlled trial. So then perhaps we should rely a little bit on the real-world evidence that we're collecting. This is an example of one of these guidelines that I just mentioned, the Surviving Sepsis Campaign Guidelines for Children. And one of the recommendations is on what first-line vasoactive kids should be started on when they have septic shock, whether it should be epinephrine or norepinephrine. And maybe somebody would say, well, this is an RCT that we should be conducting. And I don't know that we have the bandwidth, time, money to do that RCT. We have many others that we need to do. So perhaps we should be looking at the evidence that we have already. This is from a data set from over 3.6 million encounters that we collected for our Phoenix sepsis definitions. And out of those, we have thousands and thousands of kids with vasoactives. We know which vasoactive they got first, which one they got second. We know what their conditions were at the start of those vasoactives, so we can adjust for confounders, do propensity score matching, whatever technique you want to do for advanced causal inference analysis. But perhaps this is one trial that we don't need to conduct because we do have some real-world evidence, and we can save the money and spend it on I don't know, the Decadron trial, I guess, something else. We often deal with catastrophic needle in the haystack problems in pediatrics, and this is a problem that it's a real tragedy. The problem, I think, to conceptualize it, is that kids get sick very easily because they have very susceptible physiology, as I was mentioning, particularly respiratory, and they look very sick. And to somebody who's not used to taking care of a sick kid looks very sick, but they tend to get better very quickly. And you don't have to do much to help them. You just support them a little bit, give them some fluids, give them some respiratory support, and they get better. And so people get used to this idea of, oh, kids look sick, but then they get better, so I shouldn't worry too much. And so oftentimes what happens is when a really sick kid shows up to a place where they're not used to discriminating sick from very sick, these kids get missed, and there's delayed recognition, delayed diagnosis. And this is one of the tragedies of pediatric intensive care, is when you get a call from an adult emergency department 2 hours away, and you have a previously healthy kid who's now basically dying from septic shock that was completely unrecognized. And this also happens to us in our hospital. Sometimes, especially in the winter months, we have a surge of patients. Our inpatient wards are full with patients. Clinicians are running around like chickens without head. The nurses are stretched thin. And so we miss things. And some of these kids get really, really sick while being admitted in the hospital. And then we get rapid response. And the ICU goes up to see these patients. And you look at the patients, you're like, how did this get missed? But that happens. And happens not only to us, but in most children's hospitals. And so an example of this is delayed recognition of sepsis in the pediatric ward. And we had a big problem with this in our hospital at Lurie. So we took this as a learning health system problem that we needed to solve. And we took this sort of classic approach of the learning health system, of identifying the problem, generating some data insights, and then implementing a decision support tool. We collected data from our electronic health records over almost 50,000 patients. We developed a supervised machine learning model for prediction of sepsis. We had different thresholds that were developed in concert with what the clinical workflows were in the inpatient ward, so that we would have the right sort of number needed to alert to adapt to the existing workflows. We tested this prospectively for over a year, performed really well in the background, so we implemented it in real time scoring with a clinical decision support tool and a best practice advisory in Epic. But then the other thing that we did that I think made the whole difference is that we actually had co-design sessions and sort of brainstorming sessions of how do we actually implement this in the clinical workflow in ways that it's going to be used by clinicians. It's not just an alarm and alert that's just beeping there in the background, but the nurses, respiratory therapists, residents, physicians were able to put their input in of saying how they would like this to be used in real time. And that led to how we rolled this out with our educational modules and simulation, et cetera. And I think that was the crux of the success of being able to reduce our sepsis ICU transfers by 46%. And again, I think when we're thinking of this learning health system approach, it's the combination of the machine learning and the data science, which is the fun stuff, and the CDS tool design, which is the techie stuff, which is all really cool. But really, where the rubber meets the road is on actually developing these clinical workflows with the clinicians, so that this data is actually used. You can have a perfectly performing model that is not used at all, and it will be 0% effective. And so finally, I think data science and collaboration is what is going to help us move forward. We heard from the Bridge2AI Chorus AI project. There's two pediatric ICUs in that consortium. The NC3 data set also had pediatric data. PedsNet is a PCORI-funded pediatric data collaborative. And the two that I'm going to speak briefly about are the PQ Data Collaborative and the Pediatric Sepsis Definition Task Force. The task force was first convened in 2019, and we were tasked with redefining pediatric sepsis. And the way we decided to do it was developing new criteria using a machine learning approach. So we went out and actually pretty boldly said, let's collect all the data that we can. And we ended up collecting data from 10 sites from around the world, including Colombia and Kenya and Bangladesh and China. And we collected data for over 3.6 million pediatric encounters, which, by the way, tripled the Sepsis 3 adult data set, just saying. And that was what led to the development and validation of the Phoenix criteria. So again, I think there's a willingness to collaborate, a willingness to have representation in this data collaboratives, and I think this is a sort of a sign that we can get this work done. The PQ Data Collaborative is in the U.S. It's from centers from across the country. We're 18 sites. We've built this one cloud database where we have EHR granularity data. We don't have waveforms or images yet, but our focus has been on clinical data from the EHR. But we're currently at 150,000 patient encounters, but we are estimating 350,000 encounters by the end of this first wave of data submissions. Over 2 billion rows in just our measurements table, so a lot of data, and highly representative in terms of age distribution, racial distribution, et cetera. So we're very excited about this work, and this is just one small example of some of the work that we're starting to do with this, which is just looking at how frequently complete blood counts are rechecked in patients in different units. The different colors are different units. The x-axis is the hemoglobin level, and the y-axis is the number of hours between complete blood count checks. And you can see there's, these 4 units have completely different ways of doing this. And so Adam Dzorny and Serene Shah, who are the gentlemen pictured there, are studying whether there's a better way of timing when we check these labs, because as you can imagine, kids, if you check labs very frequently, they get anemia, and then it's sort of like a vicious cycle. So just as, not a tremendously, earth-shattering machine learning modeling, but just simple stuff that we can do with the data that we already collect. So I think very elegant way of showing that we can do a lot of things with good data. So in conclusion, children are not little adults, but we often pretend they are, and we shouldn't. And in data science, this is important. We have low amount of traditional data, but we have lots of real-world evidence. For the needle in haystack problems, the machine learning and workflow approach is what's going to get us there, not just the machine learning alone. And data science and collaboration will help us move forward. So again, pediatrics needs to build their databases too. And thank you very much. Thank you.
right. Been a great session so far. I just realized in my haste to get started and with all technical problems, I forgot to introduce myself here, like who is this guy? I'm Ashish Khan, I'm the outgoing chair of Discovery. I will say that I want to, in addition to thanking speakers, I want to especially thank Smitty Hefner here, who's really spearheaded our data science campaign. You guys seen all the new manuscripts that have hit critical care medicine this week, and on a round of applause for Smitty and for all of his work. All right. Last but not the least, we have Rishikesan Kamaleswaran from Duke University, who was in the middle of some traffic issues, but he's gotten here and he looks great. And Rishi, we're looking forward to your talk.
All right, thank you so much, and apologize again. Little rain just brings chaos everywhere. So I am going to yeah, I got it. Yeah. Okay. All right. Okay. So I'm going to be talking about some of the critical priorities for data in critical care. And I'll start off by, really emphasizing, as the other speakers had really described, there is a critical need for us to talk in a common language. And as many sites now start to introduce data science and data capabilities within their electronic health systems, I'm sorry, I'm going to just stop this. As they start to introduce more of these data science methods into clinical workflow, it becomes really important that what is learned at one site can actually be generalized or transported to other environments. And where we have the biggest challenge right now is in continuing to follow a pipeline where we have different vocabularies, different terminologies for essentially the same data point. So there is this critical need to standardize and speak in languages that are the same. I'm not sure why this is continuing. Yeah, it's just advancing by itself.
You keep talking.
Okay. All right. So as we start to think about what this means in terms of critical care, we realize that unlike a lot of other general health systems, in critical care, there is a slew of different data elements that are just very unique to each institution. There are flow sheets, there's different sets of measurements and observations that each institution may prefer to characterize in their own ways. And this has become really a challenge for when we want to now develop artificial intelligence methods to learn to utilize data from multiple institutions and multiple sites. And as pictured over here, we have this beautiful robotic system which is caring for a sick patient, and the DALL-E decided that sick patient was also a robot, and there's a lot of waveforms that are coming out of that robot. So of course, what does this mean as we start to build in our AI ML solutions? The rise of wearable sensing and remote monitoring, has made data just much more plentiful. We have now not only measured human-derived data, we have machine-derived data, and then we have imaging data. And all of these are starting to build on top of each other in ways that are now amassing volumes into the petabytes or the multi-petabyte range. We have challenges as we start to integrate and bring towards a system where there is inherent interoperability. And then, of course, there's, as Dr. Sevransky and others have discussed, there's this need for data-driven decision-making. This is a challenge. How do you present clinical decision support, as Nelson had pointed out, at the point of care? That is a really challenging proposition when data is characterized in all these different ways and different terms. So part of the, how do I get this moving? Is it right? Sorry, the slide is not advancing. Okay, so we'll go to the next. So as we start to think about these deployments and implementation, we not only have to deal with the complex data challenges that we face, we also have some very critical ethical and privacy challenges. Data, especially as it continues to be amassed, has potential for all sorts of PHIs or identifiable information to exist in a slew of different data fields. These include flow sheets, where sometimes you see, Dr. So-and-so told me to put this in at this time, and so I put it in, and here's the name. So there's a lot of these information that not only is integrated, but also is available broadly. So yeah. Okay. It's not. No, it's not. Okay, 1 second. I think there's two. There's two things. Yeah. Okay. Yeah. All right, so I'm just going to talk about the next slide. So as we start to build more and more of our data algorithms, the questions around privacy, confidentiality, and then proprietorship. There's critical considerations around who owns the data. Is it the patient that owns the data? Is it the institution that owns the data? Or is it the researcher that's grabbing this data that owns the data? So as we start to think about privacy, confidentiality, proprietorship, all of these are advancing more and more critical considerations and critical problems that we just are not able to really fathom without having that infrastructure in place to provide us that level of reasoning. So the question is, what do we do, and how do we try to approach this grand challenge? So we had a lot of discussions on consortia, things like Bridge2AI, the SCCM. Oh, perfect. All right, so that's fine. I'll just check on that.
I don't know why it's not.
Okay, maybe I can do. Oh, sorry.
No, it's not. Why is it not going to percent remote? That's the problem.
Yeah, so as we start to have all these different considerations, the critical questions are around how does this relate to actually bedside use and the complexity of acute illness as it manifests at the bedside. And I had this really nice image of one of my favorite slides that's actually in a paper that Dr. Claremont and Dr. Ju had presented, where there's this nice curve of distress. As patients go from a state of health, baseline health, towards a state of distress, there is this opportunity region right in the middle, where if you can capture that opportunity region, you can actually potentially reverse that course of acute illness and bring that patient back to baseline health. So as we try to understand what data elements are actually available in that island of opportunity, as I refer to that, the question is, what is causal, what's not causal, what's potentially available at the time that we can make these decisions. Unfortunately, many of the data elements that are captured in the EHR are actually anti-causal in terms of when you go back to model them. they often are recorded after an event has occurred. And they're often recorded after, maybe minutes or hours potentially after that event has occurred. So when you go back and you try to model that within a predictive model, and you naively assume that the data was available at this time for these sets of conditions, it becomes a very difficult problem to generalize, to implement it, because that anti-causal fundamental nature.
Should work.
Okay, thank you so much, guys. Is just not not there. And this is really that critical zone. So as we start to see what is available to us at this time, it's really important for us to make sure that we judiciously review every element as it's in the flow sheet or in the EHR system, to make sure that the data available in this opportunity, or this island of opportunity, is actually something that can be used in prospective work. So there's been a slew of discussions, as many of you may have seen, on the promises of AI for critical care. One of the topics that's become very popular is this notion of a digital twin. You can imagine that you have a patient constructed completely in silico, and you modify different tweaks or levers of that patient to try to see if this drug will work and if this intervention will work. And all of these require a very sophisticated combination of different levels of optimization, of different levels of simulations. But we're still quite far from actually getting to the point, at least within critical care, of creating a really robust in silico model that can produce simulations and generate predictions based on this notion of a real-time input. And one of the great examples that we saw was actually this paper that was published in JAMA, which showed that this hurried and sloppy implementation of AI or algorithms into the medical record can actually be harmful in many cases. And the most popular example was the EPIC sepsis algorithm, which had lots of publications and so forth. But over-reliance on these models without critical evaluation of understanding what are those fundamental building blocks and components that are going into these models lead us to this state where we blindly trust the model and just say, well, we're just going to, this said this, and I'm just going to say, yep, okay, just do it. Just don't bother me right now. And that's the pitfall that we may all fall into at some point. So the loss of human oversight can create very dangerous situations, and this is very critical. And if there are those of you who are young investigators in this audience, this is your moment to shine. This is your moment to go to your CMIOs and ask them, what algorithms are being deployed for my patients? And how do I vet these algorithms to make sure that I understand how those alerts and those prediction models are being generated so I can trust that they actually would work well as I intend? And this is your moment to potentially modify and change and introduce cultures of change. As Nelson had really nicely said, that clinical workflow, or the implementation at the clinical workflow level, is really the most challenging aspect of all of this work. No matter what language we speak in terms of our underlying data infrastructures, no matter what sophisticated algorithms we use, if it cannot be deployed at the point of care to improve patient care, is it really worth it? So that's a question I want to leave it to all. Thank you so much for the opportunity, and thank you for having me and accommodating all these technical snafus.